1800s, and it's basically mapping the soils, landforms, and making the inventory of what the land is made of. Is it deep? Is it shallow? Is it clay? Is it sand? All those kinds of characteristics, and doing an inventory for hopefully the wise use and management of land for agricultural purposes initially, but now it can be applied to just about any field for what is that land made of, you know, for vegetation, for hydrology, for all kinds of, natural resource management. So that's what a soil survey does, and then the NRCS has been around, started out as a soil conservation service in the 30s. With the Dust Bowl and the severe water erosion, particularly across the country, but in the southeast, that we realized that our land was degrading rapidly, and we needed to try to come up with some better understanding and practices and encouragement for better land management to feed our country and supply our resources from our land. So that's the gist of soil survey. I have a couple co-workers here, Kathy and Jackie, and they're here for getting the experience and seeing this place and observing the landforms. It's a very interesting place. I'll start out with the handouts. So here's the cover of the PowerPoint. There's a scale on there, 1 mile. So we are right down below that little 447. We're standing right in the blue, okay? And right where the blue forks. So part of the blue goes through the weir down through town, and that weir controls the flood water and shunts it over to here to Lindo Channel, so downtown doesn't flood. And then if Lindo gets too full, that water gets shunted into the Sycamore Diversion Channel. So you're at the kind of the head of the flood control structure for the town of Chico, just to understand that. So that big ditch you drove across coming in, that's not natural. That's an Army Corps engineer that takes water around town to Mud Creek, that whole big levee structure all the way back to the river on the west side of town. So we're at the headwaters of the flood control structure. So this map, basically the colored polygons are the alluvial surfaces of Chico Creek, meaning that the stream deposited these surfaces. And we're going to look at an age sequence as we progress in this first part of this tour. And we're going to start in the youngest and progress to the oldest, and then get up onto the Cascade foothills, the bedrock, okay, above this fluvial system of the creek. So that's going to be kind of an overview of the bigger system here of the Sacramento Valley, transition to the Cascade foothills. And then the second part of the trip, we're going to come back to our cars, regroup, drive to the Horseshoe Lake parking lot. There's restrooms there. Everybody can, gear up for the heat today, drink, eat, and then we're going to walk from there on up to Bear Hole and look at the bottom of the canyon and apply what we've seen here this morning. Okay, so that's going to be a little more of a freestyle walk. But this first part, we're going to kind of see it all and hopefully embed the looks and the feels and the characteristics. So then behind this map is the sequence of the sites that we're going to visit. So you see soil profile boxes, and they might not look like much to you, but if you look at them, they start to look different. And then the associated, a representative site picture, which is a big part of how we understand land and model it and kind of put the geomorphic puzzle together. So the vegetation is kind of an easy handle for people to see what I'm talking about without digging pits and being soil scientists. You can recognize the trees, and I often just use trees because they're big, people can see them, you don't have to be a botanist, but they are telling you what's going on this sequence, okay? So there's this full sequence of the sites, and even a little bit more just for enhancement to the ridge top on the Cascade foothills. And then this block diagram comes from our Butte area soil survey manuscript. There's the link up on top in red. And then it's got some extra notes to try to summarize some of the concepts within this area on this block diagram. So you can see Route 1 is outlined, and then Route 2, and we're down at the beginning of Route 1. And then just for a nice simple model that I think you're going to find and recognize it works pretty well early on and then later as we go up in the canyon is this sequence of alluvium of basically think like a staircase. Treads, risers, treads, risers. So as the creek is dissected down lower over time, it's left its older surfaces above. So we're going to climb this ladder of surfaces from Chico Creek. Okay, so this little model here is, you know, very simplistic, but you're gonna see it's very very useful, and it's universal. Where water flows, basically this is going on. So I'm going to be talking about treads and risers and recognizing them in the field. So as you may have lived in Chico for decades, and I think it's going to give you some nice context as we move up the canyon bottom, why certain settings all of a sudden pop up and little slopes happen, and you'll recognize that, and as well as in conjunction with this depiction of these surfaces that we're going to talk about. Okay, so that's about it for your handouts, and now I'm just going to go big picture before I start zooming into right here. So this is the Butte soil survey was published, and we made a general soils map, which is kind of an older tradition to try to simplify the area because of the complexity, especially an area like this is very complex. California is complex in general. It's got a lot of climate variability and a lot of geologic variability, and that drives soil variability. This isn't Iowa. This is a very interesting place. You all know, you drive around and you see different scenery and different vegetation, different looks, different crops. It's a very diverse place. So anyways, we are in Chico, and we're at this interesting place. In this interesting place, we're at the juncture of three of these big broad colors here. So the purple is the alluvial fan of Chico Creek in this case, and then so this is the Chico Creek fan, and then there's the Butte Creek fan, and that's where the really nice orchard soils are outside of town, and as well as town. Think of campus, Lower Park, really productive soils, big valley oaks. Valley oaks are a signature of really big, deep, productive soils. So that's the first tree use. And so then we have this redder color, which is the older alluvium. It used to be young and happy and productive, but now it's dissected high and dry, and we're going to see how that has progressed in soil formation to make a whole different environment, a whole different soil, a whole different plant community. Okay, and then we're going to progress up onto the tan, which in this case is the Cascade foothills. That's the Bedrock foothills, the volcanic foothills, the southern extent of the Cascade Range. Okay, so in this short walk, we're going to see those three things, and then sub-entities of them. So just looking at this map, so here's Sacramento River's here over at the edge, and there's Glenn County. And so that's the Sacramento River floodplain, that light blue. And then you have this big blue abyss. Anybody know what that is? That's the flood basin. That's the Butte Basin, the clay where they grow the rice. Okay, and it's and as I think about that lately, especially driving around looking for birds, that not a lot of people go out there. It's probably just birders and rice farmers. It's right there, but it's not a destination. But it's a big, vast sea of generally really heavy clay. Okay, and so then the purples are the nicer, younger alluvial fans. The reds are the older alluvium, and then you have kind of the same sequence here. Here's Oroville, so you have more of a Sierran sequence down here. So you can kind of see that these brighter colors are the Sierra Nevada range, and then these cooler colors are the Cascade Range. So right around here is the juncture of the Cascades and the Sierra. Okay, so that adds a lot more diversity, geologic diversity. So you're at an interesting place in that regard. So here's Lake Oroville, the Feather. So there's the Feather River fluvial system that is different than here, a much bigger system, different parent material, different ages of things, and there's the Feather River floodplain in it going down from Oroville down past Gridley. So anyways, you got your Sierra Nevadas down here, your Cascades here, and then they're corresponding like alluvial deposits in the valley. And what I will say is Chico Creek is, and a lot of these bigger creeks they're interesting that they start out in volcanic Cascade country, And then they have cut down through the volcanics to expose the Sierran bedrock up in the canyon. So when we look at the rocks here, we're looking at a mixture of the two mountain ranges. Make sense?
Can I ask a question? So why is there clay? What's the difference between the clay? Why is there clay on there and real rich soil right next to it?
That's gonna be the main theme, hopefully.
Okay.
What I talk about is the energy of the water that deposited. High energy makes big particles, low energy makes small particles. Okay, so the flood basin was a big old tule swamp where the channels were just lazy and moving around and only carrying suspended load, muddy water. That water dried out, evaporated, and left those fine particles. It wasn't moving fast enough to carry big stuff. Make sense? It's all about the energy of the water in alluvial deposition. See, it's simple, right? So now, with all that we're going to see. So, just thinking about this age progression and trying to get it across to other people that aren't geomorphologists. Just think of the life stages of a human. Okay, this is the infant, and we're going to go see the old 90-year-old. Okay, on the way. So this is the young one. This is very active. High energy, okay, get to the energy right away. Look at the size of these rocks. And also, look at how they're kind of graded. You don't see too many bigger than those, okay? So it's telling you there's some regulation of energy here, okay? That it's not moving stuff bigger than that. But it's pretty rowdy, it's moving a lot of rocks. Obviously it floods, and often within the floodplain, you'll often have bar and channel topography. And you'll often have this very distinct vegetation community, and in this case you're going to have alders, sycamores, cottonwoods that are adapted to this really dynamic flood zone. Okay, this is where it's going on. A lot of species are not adapted to that, so there's a specialized vegetation community to deal with the dynamics of flooding and material moving around. So what you have is these are channel deposits. A couple weeks ago, water was racing through here, moving these rocks, and then within a floodplain, the channel will migrate back and forth over time due to a lot of different reasons. And so as the channel migrates away, then lower energy overbank deposits will come and bury that because now the channel is somewhere else. So that's what we're looking at right here, is this sediment. Even though it's pretty coarse, it's pretty much sandy loam, very fresh stuff. This is the overbank deposits over the channel deposits. That's a theme we're going to see in these four surfaces, okay? That this arrangement is maintained into these older surfaces. So this is the overbank deposits, in this case very fresh, sandy loams, very low clay. It hasn't been here very long. It kind of looks dark because it's moist, but that's basically just the mineral color. That's not really black organic matter that's accumulated like we're going to see in the older surfaces. So this stuff is very fresh. You can see it could be very transitory and be moving away, in the next flood. It might stick around, grow some grass. It might not. It's all, it's a crapshoot in this environment. It's a very dynamic environment. So anyways, you have the theme of what we're going to see in these alluvial surfaces is channel deposits buried by overbank deposits. And that's generally pretty fortuitous for plants because they can germinate in this stuff versus that stuff. And this is usually caps off the channel deposits. Okay, what do I want to say? Yeah, about rocks. Anybody see any rocks they know that they can identify in here? And there's some clues as far as shapes and colors. Okay.
Marble, granite.
What's that? All you Chicoans.
Granite.
Lovejoy salt from Bear Hole. Okay, that's where we're going today at the end of the day. You can see it's still got some angularity to it. It hasn't totally rounded because it hasn't traveled that far, and it's also pretty hard stuff. And then you have a lot of andesite. Okay, there's more of this than anything. This is from the Cascade mud flows that we're going to go visit. Okay, and this gets pretty rounded. It's probably traveled quite a bit farther. And then we have some special rocks. What's that? What are those white things? Quartz veins. What does that mean? It was metamorphosed. That's from the Sierra Nevada. The volcanics were not metamorphosed. They're younger. So this is the quartz veins that the gold was in. Okay, so this is Sierra rock. So like I said earlier, the creek up above Forest Ranch, it goes through a stretch where it cut down through the Sierra rocks, and so this is one of those that made it down here. So that's just a little bit of playing around and looking at kind of the watershed source for what you're looking at, and just to, you know, hopefully tie it together a little bit. So pretty rounded, pretty sorted, and also graded by size. And as we travel up the canyon, you're going to notice that the rocks get a little bit bigger. Make sense? Because we're getting up into the higher energy, steeper corridor. It's getting flat here. So this is where the creek is coming out of the confinement of the canyon and getting to spread laterally to make the fan. That makes sense? So that's going to be a big part of what we look at today, is starting out in the valley where things are not confined. The creek was able to move back and forth without any restrictions. And as we get up into the canyon, we're going to see what is left from where it did not have that lateral freedom. Does it make sense? Okay. So surface 1. That's enough, huh? Need a little more fun. Okay. So we talked about treads and risers, the staircase. So now we're going to move from this tread, climb a little riser to the next tread. Okay, this is surface 2. It's green on that map. We got out of the blue onto the green. This is a managed, you know, mode recreation area, but it's still giving us some signatures here. Okay, now we're looking at valley oaks. Okay, we didn't see valley oaks in surface 1. Valley oaks are in it for the long haul. They're not adapted to the dynamics within the floodplain itself. So they like to be a little higher, a little more stable position. There's also sycamore. Sycamore lives in both of those systems. There are no more willows, no more cottonwoods. Okay, so we've left that riparian community, and now we're onto the stream terrace, which is slightly older. Okay, so now we're looking at this soil, and can I see that first one? Oh, just want to hold that first. Okay, so there's sunlight here. So here's surface 1. Very fresh. Hasn't been there, hasn't had a lot of organic accumulation. Here's surface 2. You can see how biologic this has gotten. Okay, much darker by organic matter. Again, the colors aren't dramatically different, but you can see that darkness. This is nice stuff. Okay, this has been stable. It's been here long enough, supporting valley oaks, grass, shrubs, and accumulating organic matter. And also, the biologic activity that goes with that is starting to make these PEDs, or aggregates, okay? Where this stuff is just still single grain. It's pretty inert, okay? It's just fresh sand. This stuff is really becoming a biologic soil. You see those nice crumbs and pieces, and that's due to the glue and the root exudates and the microbes. That's a really nice, happy setting soil. That's showing you good structure, good organic accumulation, and we've got 2 there. And then just to stick on that theme of, these are nice overbank deposits, over sandy and gravelly, channel deposits like we saw earlier. And so this is the higher energy subsoil with the gravels in it, and you can see how loose and structureless this is, so that soil formation has not penetrated that deep in this yet. Okay, so you still have this kind of fresh, initial, inert, coarser subsoil under this, but this stuff makes really, this is the money surface as far as vegetative productivity. This is why Bidwell settled here. is these soils on the fan and through Lower Park, through campus, just know the Valley Oak signature, as well as the orchards. This is really good, happy stuff. It's young enough that it's not all weathered out, and the nutrients are still releasing. It has a lot of organic matter. It's got nice permeability for air, roots, and water. So this is the real nice soil of the fans around here. And we're up at this proximal part of the fan, the high energy. So up here, they're a little coarser, and as you go out in the valley, that energy decreases and they become a little bit finer. Less sand, more clay. As you go out to the basin, where it is pretty much all clay and silt, in that whole gradient of deposition by the energy of water. So you're kind of in the high energy zone of this much larger system going all the way out to the basin. Make sense?
Yeah.
So nice stuff. Big trees, big soil. Any questions? This is the good stuff. And
He said, look at the slope, how uniform the shape is.
And notice around the top. Surface 2 to surface 3, okay? So this is an older surface deposit from Chico Creek. It used to be young and fresh like that, now it's getting old. So what do you see in that? Red. Okay, oxidation, okay? So this is long-term soil weathering. You're also getting kind of angular structures. See how sharp those corners are? So this is those same soils sitting here for hundreds of thousands of years and weathering into loamier textures with more clay. And somebody asked about the clay. So those sand particles start to weather down and break apart and become clay particles over time. And then the iron oxidizes to make this red color. So you kind of have this leathery look on here that is even showing how the clay then moves through the profile and collects in the subsoil. And that's a real important indicator for showing the age of the soil and how much development has happened. And so this is you know, we started out in an infant, and then we were in a toddler. Now we're in something like, you know, a 60-year-old. Okay, we kind of made a big jump from there to here. But this red stuff, and it's not so sandy and gritty anymore. It's got a much finer texture with a lot more clay that becomes a little more sticky and a little more plastic than what we've seen. But anyways, just the redness and the amount of weathering that this is expressing has changed dramatically from what we've seen so far. Make sense? I'll just do the surface over there. But anyways, I just want to show the red subsoil, and then we're going to stop just right over here and kind of do our same little routine on the surface and kind of look at the veg and topography. Soil right there.
Are you telling me that this is alluvial also?
Yes. Yep. These first four surfaces, these were deposited by the creek a long time ago. See how flat it is? That's a really good indication. Okay. Creeks leave flat surfaces. Okay. There's no bedrock, knobs, and undulations here. This is just nice and flat. So that's that whole stair-step sequence. We're climbing the staircase. Yes, you can feel a little bit of clay. You can feel how it holds together. And feel how smooth that is compared to that gritty stuff.
Yeah, it stays on your
finger. It stains you. Nice red stain. Again, just to re-emphasize, notice the flat surface. Okay, that's a good key to corresponding profile characteristics that we know. Yeah, we got these old overbank deposits over the old rounded channel deposits. Okay, so we're bringing that heritage through time here. Make sense? And this is a very enchanted blue oak forest. This is kind of a rare remnant. You don't see a lot of this around.
What kind of pine? Is that a ponderosa?
These are grape pine.
Those are
Grape pine. Yeah, you might find a ponderosa come down. We'll see one like at day camp, but they usually don't come down this far. And that's a happy grape pine.
Yeah.
Living in pretty good stuff. No restriction here as far as depth. Do not need the waxy on the bottom.
Where's the poison oak?
All of that stuff right there without the leaves.
Oh, without the
Yeah, that's some pretty happy poison oak. All of that. Up there when we go to the cliff.
Is the north end of Chico, the soil's
A little bit of a subriser to the higher, more stable surface floor. Those trees are growing right at the shoulder, okay, where it's convex and crown and it drains better. Okay, they're not growing here or above where the water just sits more continuously.
All those up there you're talking
No,
about?
this tree here and this tree here. Just talking very locally. So, you know, that the right year, the bird dropped the acorn and it grew. But generally, you're not going to have them out here. And look at how it grew on that shoulder where it drains. It's convex. The water doesn't sit there all winter long. Blue oaks do not want to be in water. Topography.
This is surface 4, mound
Haven't
swale.
seen that yet, huh? Look at that. See that? The veg is showing it. These concavities are shallower with wetter veg. That water table exists all across here, but it comes up to the surface in these concave swales. It comes up near the surface on the mound. But look at the veg difference between the two settings. And this is about twice as deep as that to the hard pan. So the grass grows taller on the mound because it's deeper soil, right? Agree a little bit.
Yeah.
So it's just an interesting tie-in to the whole landscape evolution of what a creek does upstream and what it produces downstream. Especially when you have diverse substrata it's working it with. It's not all one kind of cake up there. Make sense? Okay, you guys don't have to move, and I'm not going to make some over here. Now I'm going to blow your mind. Look at that.
nice stuff.
This is heavy clay. Feel that.
Oh,
Feel that.
oh, it is heavy clay.
This is very different than anything we've seen. That's heavy clay. Clay and silt. No sand, okay? Feel that. This is,
Wow.
you can just like
Very
walk
sticky.
around like
Very sticky.
being like a stress ball with these whole
Yeah,
things.
yeah.
Feel that.
Oh, okay. Why not?
Get a little on you. Okay, this is like the clay that's out in the flood basin where they grow the rice. Up here, there's a little bit of it. And in here, it's in this black stringer. It's on your block diagram. It's that black polygon. It's black on the other map. And it kind of swings around here, goes around that power pole, and goes north up into Bidwell Ranch. So look how different this is from this, right here, in this short distance.
The color is different too.
Everything's different.
Yeah.
The composition's different. Much different.
And what's the reason, Andy?
Yeah, that's tough questions. Okay, kind of a knee jerk is the clay is really low energy alluvial deposition. So just like really slow water moving through here, but because it's up on slopes and other things, there could be a whole set of really dynamic factors, including volcanic ash deposition and remobilizing into these back channels, low energy deposition. Just the water wasn't moving really fast, so it was kind of like a, you know, like a milkshake slurry that when it dried out, this is all it left. And this is very wet. This is much wetter than this. So that water on this pan is rolling off, and you're in a concavity that is where this water collects, and it's slowly moving out through the soil and with kind of a man-made drainage channel through this clay swale. So this is where, if you find a vernal pool in this, it's going to be bigger and wetter. Okay, so as you know, hopefully there's a couple different scales of vernal pool sizes and flashiness. This would be a long-term, very wet vernal pool. Okay, because you're in clay, that's where the water's collecting. Up here, you might have a little pool that, yeah, it's wet for a little bit, but then it dries out. And you'll see like a red soil versus this dark gray soil.
Just that standing water over there.
Yeah, and this is a really interesting, look at this on Google Earth, the way this clay kind of, you know, makes this branching linear feature here. And a lot of times you can read the vegetation. There's no star thistle in this. Star thistle will not grow in this wet clay. You have a bunch of geophytes, okay, and ryegrass and stuff that's adapted to really soak in wet conditions. So the species that live there do not live here, and vice versa. And sometimes the right time of year, and I'm sure you've all seen it, was maybe a little further along in the winter, you get these geophytes, these bulb plants here, and they all get that little rust fungus on the tip, and this will look orange. You ever seen that?
Yeah.
It's pretty cool. It shows you where the clay is. That fungus feature on the plant shows you where the clay is. And it is. It'll be like a very abrupt boundary of orange, you know, tip geophyte. So anyways, this is important to know for engineering. If engineers want to know anything about soils, is where is this stuff? This stuff wreaks havoc on foundations, roads, railroads, structures. It shrinks and swells. Everything's swollen now. You come back in the summer, you're going to see cracks that big. Okay? It expands and contracts tremendously. So on engineering features, it wreaks havoc. When you drive out into the basin, the mother lode of the clay, look at how much railroad base they have to use to get the insulated above that clay, so the trains don't rock. Even the roads, you'll be driving on the fan, all of a sudden you hit the basin, and all of a sudden you're driving like this because the clay's moving the road around. And you can see how much road base they have to build up to try to insulate from that dynamic. It wreaks havoc on engineering structures. In Texas, they have to water foundations so they don't shrink and swell.
Yeah, that happened. One of our contractors was talking about that. They had to put somebody's home in, with clay, and it was breaking his foundation.
Yeah. Look at the slope we just started to climb from those flat shreds of the fluvial surface of Chico Creek in the Sacramento Valley. Okay, so this is bedrock. This is volcanic bedrock. This is volcanic sandstone. Okay, this is bedrock. It's you can see I can break it up. But in place, it's pretty tough, it's intact, and this little next sequence is going to be a very condensed sequence to try to describe the whole sequence on the canyon slopes without walking up one of the big slopes. So this is one of the Tuscan units, and it's volcanic sandstone, and it's very well sorted. There's, you know, these rocks have tumbled down, but you can see within this stuff there's no rocks, okay? It's just sandstone, okay? This is kind of one of the prime beds of the Tuscan Aquifer. This stuff holds water because it's well sorted, so all the sizes are about the same size, so that makes a lot of pore space, versus if you have big, you know, beach balls, bowling balls, baseballs, golf balls filling the gaps. This is all the same size, so it actually holds a lot of water. So as this continues out under the valley, this is where our aquifer is. Make sense? A lot of people have a little hard time getting over aquifers and bedrock. This is a good example of that.
So this bedrock is underneath the aquifer over in the valley?
This whole Tuscan pitch here continues out under the valley. Okay, and in places it's interrupted because the creek is cut through, but in concept it goes all the way to the river. Okay, so this, and right here is where we walked above the line where it's buried and now it's exposed. Okay, and the creek has been through here, but it's sloping enough so any trace of creek deposits have not retained in the couple million years. So this stuff is just basically the thin, very harsh soils here are weathering from this stuff right here. Make sense? So this is the skeleton of the earth right here, the exoskeleton, and that's kind of the deep fill sediment right below us. And see how flat that is, and see how sloping this is. That slope break is, you know, a huge indicator. Make sense? And asking about the trees, just look how much drier it is here, okay? You know, the water has already moved on through here. You know, due to the slope, you're also south facing and you don't have much soil here. So this isn't as muddy as what we saw. Make sense?
Is there aquifer right here And if so, how deep maybe?
This is the material the aquifer's in, and particularly as you're out in the valley.
So is there aquifer right here?
Underneath?
Yeah.
Yeah.
Maybe how deep?
How deep to it? You're going to have to talk to a hydrologist.
Guess.
How far down in the valley, how far down is this bedrock?
Well, as you can see, this pitch maintains. So you can kind of do the math of this gradation so it gets deeper as you go out. And I got a couple cross sections since some of you folks are dialed into this, so maybe we'll look at the top or later. But I don't have the numbers in my head. Well, it depends on where you are. Of this Tuscan sequence, so you're seeing sandstone, you're seeing conglomerate, we're going to see something else right there. So start looking at the stripedness in the canyon, and you can start going, oh, there's bedding differences in this rock strata that produce different soils, different slopes, different vegetation. Okay, and we're seeing that right here. Does it make sense? And these are sorted, and I'll get to that next.
What volcano might be the source of the
Mount
volcano?
Yama,
Which was where?
above Jonesville. You ever been to Humboldt Summit?
Yep.
You are at the edge of the caldera there.
Oh, wow. How do you spell Jana?
Y-A-N-A.
Wow.
Okay, now that's the mud flow. That's what I use just as a simple term. More technically, it's andesitic tuff breccia, but I won't torture you with that. This is what I call mud flow, okay? And this has all kinds of different rock sizes and shapes. See that? There's some angular ones. They're all over the place as far as sizes. So really no sorting. This is kind of a chaotic slurry that came from Mount Yama. And there's probably a lot of different geologists that might have different stories. This is my story, and I had it approved by the guy that discovered Mount Yama. That these mud flows came out of Mount Yama, and a lot of people think of lahars as just kind of debris flows on the side of a volcano. And this stuff there was actually water in the volcano, magmatic water. So this was erupting as hot cement. Okay, not lava. Okay, this is not lava. This is an ashy, tuffaceous matrix. These are chunks of lava. These harder fragments within it. But this is not lava. And so this was a slurry, like concrete. And the motion of it kept things in suspension. And then when it stopped moving, just like concrete, that's why they spin the trucks. When concrete stops moving, the water rises and it dewaters. So you would have this dewatering, and it would start to sort this material and like remobilize resorted material as conglomerate in higher energy channels, as sandstone in lower energy redeposits. And then another mud flow would bury that. So you have the sequence of deposits, and then the reworking and dewatering, and then another deposit. So when you look up at the canyons, you can see the big cliffs are generally the mud flows. That's the hardest one. It holds the biggest cliffs. And then these softer beds, like we saw, start making those more gentle slopes in between the cliffs. Does that make sense? So, you know, this Tuscan has, you know, three main kinds of rock. This one isn't very functional as an aquifer. You can see this wouldn't hold a lot of water versus that sandstone. Make sense? So this is basically the cap flow that you see on this whole volcanic plateau that we're climbing. And we're going to see some interesting rocks and sizes and differences in sizes that just shows you this was a chaotic slurry. It wasn't like a nice fluid, you know, regulated stream like we've talked about so far. There was big chunks held in suspension due to the motion.
Roughly when did the volcano be active?
About 3 million years, give or take. When I was mapping up in the woods, I kind of got a sense there's a big old volcano here somewhere, and then I thought I discovered it, but then, and Leyden had discovered it, Phil Leyden had discovered it in the 60s, and I guess he did his thesis on it, and somehow I got wind of that and went and the Chico State Library, got in the microfilm, was like, yep, he got it. He already got the volcano. But it was very unknown. It's not on a map either. You're not going to see Mount Yama on a map. You'll see Butte Mountain, which is like a satellite cone of Yama.
So you're kind of like Columbus.
That nice uniform cut represents the northern extent of where the creek has been coming out of the canyon. Okay, so now you're just over bedrock. It hasn't been there in a long time, and the whole base level was probably a lot higher, let's say 50 feet higher in the valley, you know, for that to have happened. And so since then you've had, you know, down cutting, dissections, and so pretty much any of the alluvium that was here is gone. It's eroded away because this has been here on this slope for a very long time, and this soil is kind of maybe a combination of the detritus of that as well as weathering from the bedrock itself. This is very shallow, very limiting. If you're going to know anything about soils, know how deep it is, this is about as tough as it gets. And we're going to see that up top too. This is tough ground, okay? So traditionally, again, people didn't have any use for this except grazing, okay? That's all you're going to get out of here. And then this even yields less for grazing than the surface 4 because you got all these stones. That you can put more cows on surface 4 than you can on this. And that stays wetter longer because it's flatter. So when you come out here in April, you can see this drying up. As soon as you get to this slope where the stones are, it's already drying out and it stays wetter. The grass stays greener about 2 weeks longer on surface 4 because it's flatter. Okay?
And the stones are here because of the erosion?
Yeah, they are. They are basically the lag deposit. And as we walk up, we're going to see these, you know, desk-sized stones and boulders in the matrix of this mud flow. And so, like I said, the matrix is ashy, welded ash that is not as hard as the fragments that themselves. So the matrix weathers the soil and leaves the stones as a lag deposit. So there's more stones on the surface than in the matrix because maybe 10 feet of the matrix has weathered away and eroded away. So you're looking at, you know, these were in suspension, you know, above the ground, and now these are hard. These will be here for a long time versus that matrix.
Are they volcanic too?
Yep. They're mostly andesite, you know, a lava rock, like basalt, but not as much iron. So they're grayer than black, typically in a simplistic way. But anyways, nothing fancy here. Kind of a darker clay loam, very shallow, very tough. You got erosion problems here because you're on a slope. And if we do nothing else as far as soil survey is acknowledging slopes and the potential for erosion due to that. Okay, you don't want erosion.
So the black lava rock has more iron?
Yes. And that's what makes it basalt versus andesite. Andesite's more intermediate. And then if you even less iron and more quartz, you get to like rhyolite. Okay, so there's that whole spectrum of mineralogy for extrusive rocks as well as intrusive. This will be surface boulders disconnected, right? This is harder than this. So that's weathering away, leaving these hard rock fragments.
Does that have to do with temperature?